Tonight, we're going to explore something that sits at the heart of humanity's biggest dream about the future: how far we could actually travel through space in a single human lifetime. You've probably thought about this before. Maybe you've seen articles about Mars missions or generation ships. It comes up in almost every conversation about humanity becoming a spacefaring species. But here's what most people don't realize. The answer to this question isn't really about engineering or rocket fuel. It's about the fundamental nature of distance itself and what happens when a human lifespan collides with the true scale of the cosmos. And by the end of this journey, you're going to understand exactly where a human being could reach before their time runs out, and why that boundary exists where it does. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Tonight, go outside and look up at the moon. When you see it, you're not looking at the moon as it exists right now. You're looking at the moon as it was 1.3 seconds ago. That's how long it takes light to travel from the lunar surface to your eye. 1.3 seconds. The time it takes to snap your fingers twice. The light is old, already outdated by the time it arrives. Here's another way to think about it. If you could read at the speed of light, finishing one page every light second, you'd finish an entire book before the moonlight updated. You'd have time to read a short novel and still be looking at the past. The sun is even older when you see it. 8 minutes and 20 seconds old, to be exact. Every ray of sunlight touching your face right now left the sun's surface 8 minutes ago. If the sun exploded right now, vanished in an instant, you'd have 8 minutes left. 8 minutes of normal life. 8 minutes of sunshine and warmth before everything changed. You wouldn't know. You'd just be sitting there, living your last moments under light from a star that no longer exists. That's not a metaphor. That's reality. You live in the past, not the present, because light takes time to arrive. The stars you see on a clear night are even further back in time. Most stars visible to the naked eye are between 4 and a few hundred light years away. Their light has been traveling for years, decades, sometimes centuries before it hits your retina. When you look at Sirius, the brightest star in the night sky, you're seeing it as it was 8.6 years ago. That light left Sirius when you were younger, when the world was different, when people you knew were still alive or not yet born. You're not looking at the present, you're looking at a photograph, a very old photograph. This is the part that gets me. On any clear night, if you know where to look, you can see Andromeda, the Andromeda Galaxy. It's visible to the naked eye as a faint smudge in the constellation that shares its name. Most people have looked directly at it without realizing what they were seeing. They thought it was a cloud, or a trick of the light, or nothing at all. The photons hitting your eye right now left Andromeda 2.5 million years ago, before humans figured out how to make fire, before we walked upright, before we were we. You're not looking at a galaxy, you're looking at a time machine. And most people walk past it every night without knowing. Think about that for a second. You can point your face at the sky, aim your eyes at a specific patch of darkness, and capture light that began its journey before humanity existed as a species. The light traveled across 2.5 million years of space, while our ancestors evolved from something that wasn't quite human into something that could stand upright, make tools, create language, build civilizations, and eventually look up and wonder what that faint smudge was. All of that happened during the travel time of a single photon. Andromeda's light left home when our ancestors were still figuring out how to chip rocks into blades. It crossed the void while continents shifted, while ice ages came and went, while entire species rose and vanished. It arrived tonight, at your eye, right now. You don't need a telescope for this. You don't need equipment, you just need a dark sky and the willingness to look. Andromeda is there, about the width of 6 full moons across, smeared into a glow so faint your eye barely registers it. But it's there, and the light is older than your entire lineage. Finding it takes a little practice. You look for the constellation Andromeda, follow the curve of stars, and find the smudge that doesn't look quite like the others. It's fuzzy, indistinct, easy to miss if you don't know what you're searching for. But once you see it, once you know what it is, you can't unsee it. That's not a cloud, that's a galaxy. And it's saying hello from 2.5 million years in the past. This is what observation really means. All observation is time travel. You never see anything as it is. You only see it as it was. The farther you look, the deeper into the past you go. Your friend across the room is a few nanoseconds in the past. The moon is over a second behind. The sun is 8 minutes old. The stars are years out of date. And Andromeda is ancient history by the time you notice it. The universe doesn't update in real time. There's no instant refresh. Light has a speed limit, and that limit means everything you see is already gone. Not gone in the sense of destroyed. Gone in the sense of changed, moved on, evolved into something slightly different than what you're looking at. When you look at the night sky, you're not seeing the universe as it is. You're seeing the universe as it was, layered across time. Every object broadcasting from a different moment in history. The moon from 1 second ago, the sun from 8 minutes ago, Sirius from nearly 9 years ago, Andromeda from 2.5 million years ago. You're standing in the present, looking at 1,000 different pasts, all arriving at your eye simultaneously. This is the foundation of everything that comes next. Because if light takes time to get here, if we're always looking backward through time, just by observing, then the question of how far we could travel becomes a question of how much time we have and how much distance light itself can cover while we're still alive to see it. The distances are about to get much, much larger. The distances are about to get much larger. But first, we need to talk about the speed we actually have. Voyager 1 launched in 1977. It's been traveling through space for 47 years. Nearly half a century of continuous motion, never stopping, never slowing down. It has covered 15 billion miles. That's 15 with 9 zeros. That probe has traveled farther from Earth than any human-made object in history. It's in interstellar space now, beyond the influence of our sun, coasting through the void between stars. And it has covered less than 1 light day of distance. Light crosses that same 15 billion miles in about 22 hours, less than a single day. Voyager has been traveling since before Star Wars came out, and it hasn't even covered the distance light travels while you sleep. If you took 1 breath per second since Voyager launched, matching your breaths to light seconds of distance, the probe has covered fewer breaths than you take in a single day. That's the gap we're dealing with. That's the problem. Voyager moves at 38,000 miles per hour. That sounds fast. It is fast by any human measure. A commercial jet cruises at about 600 miles per hour. Voyager is 63 times faster than that. But on cosmic scales, 38,000 miles per hour is glacial. It's effectively standing still. Let's look at something even faster. The Parker Solar Probe holds the record for the fastest human-made object ever built. It reaches speeds of 430,000 miles per hour as it skims past the sun. That's more than 11 times faster than Voyager. That's so fast, it could cross the entire United States in 20 seconds. If you blinked, it would already be on the other coast. At that speed, reaching Proxima Centauri would take 6,600 years. Proxima Centauri is 4.24 light-years away. It's the closest star to our sun, our nearest stellar neighbor, and even with our fastest spacecraft, the one that breaks every speed record we've ever set, the trip would take 66 centuries. If you launched the Parker Solar Probe toward Proxima Centauri right now, it would arrive in the year 8624. The pyramids of Giza are only 4,500 years old. This journey would be longer than the entire span of recorded human history, twice as long. The New Horizons probe reached Pluto in 9.5 years. That was a triumph. Pluto sits about 3.7 billion miles from Earth, and we got a spacecraft there in less than a decade. But Pluto is still inside our solar system. It's still part of our immediate neighborhood. At the speed New Horizons traveled, crossing a single light year would take 18,000 years. 1 light year. Proxima Centauri is more than 4 light years away. Picture this. You get in a car and start driving. You never stop, No sleep, no food, no bathroom breaks, just your foot on the pedal forever. You start driving at the fall of Rome in 476 CE. The Western Roman Empire has just collapsed. The ancient world is ending. You drive through the Dark Ages. You drive through the Renaissance. You drive through the Industrial Revolution. You drive through both world wars. You drive through the moon landing, through the invention of the internet, through every single moment of human civilization that comes after Rome. You're still driving when our sun begins its death throes billions of years from now. Actually, scratch that. You still wouldn't be halfway there. That's not an exaggeration. That's the math. At highway speeds of 70 miles per hour, driving continuously for over 5 billion years gets you less than halfway to Proxima Centauri. The universe doesn't care what we find convenient. The distances are what they are. Here's another way to think about it. Start running at a comfortable pace, 8 miles per hour. You begin running when the ancient Egyptians are building the pyramids around 2500 BCE. You run through the rise and fall of every empire, through every war, every plague, every discovery. You run for 4,500 years without stopping. You'd barely make it to Mars' orbit when Mars is at its closest approach to Earth. Not the surface, just the orbit, and only if the timing was perfect. These aren't speeds that get us anywhere. They're speeds that make interstellar travel absurd. The gap between what we can do and what we need to do isn't just large. It's functionally infinite with our current technology. We can see Proxima Centauri. We can study it. We know it has planets. We know one of those planets orbits in the habitable zone where liquid water could exist. We can observe all of this from Earth with our telescopes, but we cannot get there, not in a human lifetime, not in 100 human lifetimes. This is the central problem. We've built machines that can escape Earth's gravity. We've sent probes to every planet in our solar system. We've put 12 humans on the moon and brought them back. We've landed rovers on Mars that have been driving around for years. Within our solar system, we've proven we can go almost anywhere we want, given enough time and fuel. But the solar system is tiny. It's a speck. The distance from the Sun to Neptune, the farthest planet, is about 2.8 billion miles. Voyager 1 has traveled 5 times that distance, and it's still barely outside our solar neighborhood. The distance to even the nearest star is 1,500 times farther than Neptune. Everything we've ever done, every mission we've ever flown, every kilometer we've ever covered is confined to an impossibly small bubble around our sun. And here's the thing that really sits heavy. We're not getting dramatically faster. The Parker Solar Probe is the fastest we've ever built. And it's only that fast because it's falling toward the sun, using our star's gravity to accelerate. In deep space, away from any gravitational assist, we can't maintain anywhere near those speeds. The fastest we can reasonably send a probe into interstellar space with current technology is maybe 50,000 miles per hour, maybe 60,000 if we get lucky with planetary alignments and gravitational slingshots. At those speeds, the stars remain unreachable. This is where we are. This is the speed we have, and it's not enough, not even close. If we're going to answer the question of how far a human could travel in one lifetime, we need something different, something that changes the equation entirely. That something exists, and it's been staring us in the face for over a century. 1905, Albert Einstein publishes his theory of special relativity. It's a short paper, only 30 pages. The math isn't even that complicated compared to what comes later, but buried in those equations is something that changes everything we just talked about. Time is not universal. It doesn't flow the same for everyone, everywhere. It flows differently depending on how you're moving. This isn't philosophy. This is physics. Here's what Einstein realized. 2 observers moving relative to each other will measure time differently. A clock on a spaceship moving at high speed runs slower than a clock on Earth, not because the clock is broken, not because of some mechanical effect, because time itself, actual time, flows more slowly for the moving observer. This effect is called time dilation, and at everyday speeds, it's invisible. Drive across the country at 70 miles per hour and your clock loses a few nanoseconds compared to someone who stayed home. You'd need an atomic clock to even measure it. but push toward the speed of light, and time dilation becomes extreme. At 99% the speed of light, time runs at about 1/7 its normal rate. A clock on your ship ticks off 1 year while 7 years pass on Earth. At 99.9%, the ratio becomes about 22 to 1. 22 years on Earth for every year you experience. At 99.9999% the speed of light, the factor exceeds 700. 700 years pass on Earth for every year you live through. Let me say that again differently, because it matters. You age 1 year, Earth ages 700. You age 10 years, Earth ages 7,000. You experience a normal human lifetime of, say, 80 years. Earth moves forward 56,000 years. Civilizations rise and fall. Languages are born and forgotten. The entire span of recorded human history twice over while you live one life. This is the loophole. This is how you cross distances that seem impossible. The universe hasn't changed the speed limit. Light still moves at light speed, and you still can't exceed it. The stars are still trillions of miles apart. From Earth's perspective, you're still taking hundreds or thousands of years to reach them, but you're not experiencing those hundreds of years. You're experiencing decades, maybe less. Your heartbeat stays normal. Your thoughts remain coherent. You eat, you sleep, you read, you think. Time doesn't stop, it compresses. Every moment feels exactly as long as it always has. But the universe outside your ship speeds up like a time-lapse video. Stars are born and die while you eat breakfast. Think of time dilation as the universe's exchange rate. You trade Earth time for distance. Every year of your life buys you hundreds of light years of travel. The faster you go, the better the exchange rate becomes. At high enough speeds, your lifetime stretches across distances that light itself would take millions of years to cross. But everyone you know pays the price in years they'll never get back. This isn't science fiction. This isn't speculation. This is observed, verified, measured reality. Particle accelerators prove it every day. Subatomic particles that should decay in microseconds last for milliseconds when moving near light speed. Their internal clocks run slower. Atomic clocks flown on airplanes come back slightly behind clocks that stayed on the ground. GPS satellites have to account for time dilation, or they'd give you directions to the wrong street. The effect is real. We've tested it. We've measured it. We've built our infrastructure around it. Here's the classic thought experiment. 2 twins. One stays on Earth. The other boards a spaceship and accelerates to 99.9% the speed of light. She travels for what feels like 10 years, then turns around and comes home. To her, 20 years have passed. She's aged 20 years. She's experienced every moment of those 2 decades. But when she steps off the ship, her twin is 440 years old. Imagine watching your grandmother grow younger than you. Not in reverse, just slower. You visit her after a trip and she's aged 1 year. You've aged 10. Next trip, she's aged 5 years. You've aged 50. Eventually, you're attending her 80th birthday party at your 800th. That's not fiction. That's physics. The technical name for this is the twin paradox. It's not actually a paradox. It's just deeply counterintuitive. Our brains evolved to navigate a world where time flows the same for everyone. We have no intuition for a universe where it doesn't, but the universe doesn't care what we find convenient. This is how you reach the stars in one lifetime. You don't break the speed limit. You bend time. There's a catch, of course. There's always a catch. Time dilation doesn't make the journey shorter from Earth's perspective. If you're traveling to a star 1,000 light years away at 99.99% the speed of light, Earth still waits 1,000 years for you to arrive. Your family still ages. Your friends still die. Your entire civilization still marches forward without you. The loophole only works for you. You experience a decade or two while a millennium passes back home. It's a trick that benefits exactly one person. You can cross the galaxy. You can visit worlds that won't be colonized for 10,000 years. You can see things that humanity won't discover for 100 generations. But you can't come back to the world you left. That world will be gone. Everyone you knew will be centuries dead. The language you spoke might be extinct. The nations you knew might be dust. This is the price. This is what the universe demands in exchange for distance. You get to travel. You get to see the stars. But you travel alone through time as much as space. Every journey is a one-way trip forward into a future you can never return from. And here's what makes it stranger still. This isn't a limit we need to overcome. This isn't a problem we need to solve. This is the solution. Time dilation is the reason interstellar travel becomes possible. Without it, we'd be bound to our tiny bubble of space, forever limited by the human lifespan. With it, the galaxy opens up, not easily, not cheaply, but it opens. The question isn't whether this works. The question is whether we can build something fast enough to make it matter. So how do we measure this compression? How do we put numbers to something this strange? There's a value physicists use, a single number that captures how much time slows down at any given speed. It's called gamma. The Greek letter gamma, written as gamma, is reality's compression algorithm. It's the ratio between time as the universe experiences it and time as you experience it. At gamma equals 1, you're stationary. Time runs normally. As you speed up, gamma increases. And as gamma increases, the universe's time compresses into your time. Here's what that looks like with real numbers. At 50% the speed of light, gamma equals about 1.15. That means time dilates by 15%. For every 100 years that pass for you, 115 years pass for the rest of the universe. Not dramatic, but noticeable. At 90% the speed of light, gamma jumps to about 2.3. Time runs less than half speed for you. Your 100 years becomes 230 years of external time. The compression is becoming significant. At 99% the speed of light, gamma reaches about 7.1. 100 years of your life equals 710 years out there. You could leave Earth and return to find civilizations risen and fallen. Technologies you never imagined, now obsolete. At 99.9%, gamma hits 22.4. Your century becomes 22 centuries. You depart in 2024. You return to the year 4224. Everything you knew is ancient history. At 99.99%, gamma reaches 70.7. Your lifetime stretches to cover 7,000 years of external time. The pyramids are closer to us now than your departure date would be to your return. At 99.9999%, gamma exceeds 700. This is where it gets absurd, where the math stops feeling real. At gamma equals 700, a 70,000-year journey compresses into 100 years of your life. The universe doesn't skip those 70,000 years. They happen, star by star, generation by generation. You just experience them in fast forward. Think of gamma as a gear ratio in a transmission. Low gamma, slow speeds, that's low gear. You experience time almost normally. You move through the universe at the same pace as everyone else. High gamma, near light speed, that's high gear. Every pedal rotation, every heartbeat of your life carries you vastly farther through external time. Same effort, different result. Your lifetime becomes a fixed resource with a variable exchange rate. You have maybe 80 years to spend. That doesn't change. You can't create more time for yourself. But at gamma equals 1, stationary on Earth, you buy 80 years of universe time with your 80 years of life. 1-to-1 exchange. At gamma equals 700, you buy 56,000 years of universe time with that same 80-year life. You're not living longer, you're buying more universe with the same life. The curve is steep, brutally steep. At 99.9999999%, the speed of light, gamma, exceeds 70,000. Your 80 years becomes 5.5 million years of external time. You could watch species evolve. You could see continents drift. You could witness the birth and death of civilizations that won't begin for epochs. There's no upper limit. As your velocity approaches the speed of light, gamma approaches infinity, meaning time compression approaches total. Theoretically, if you could reach the speed of light, which you can't, time would stop for you entirely. You could cross any distance in zero subjective time. The entire universe would be compressed into a single instant. That's the theoretical possibility. Cross any distance. Travel to galaxies so distant their light hasn't reached us yet. Do it all within a human lifetime. Not because you're living longer, because you're experiencing less of the journey. This isn't speculation. We've tested this. Particle accelerators routinely push subatomic particles to gamma factors over 10,000. Particles that normally decay in microseconds survive for seconds. They live 10,000 times longer than their normal lifespan, exactly as predicted by gamma. We've already proven time dilation at extreme levels, just not with humans yet. The physics works. The math checks out. Gamma can theoretically reach any value you need to cross any distance. The galaxy opens up. The universe opens up. Every destination becomes theoretically reachable if you can push gamma high enough. Which brings us to the question that matters. What speeds can we actually achieve? Because theory is one thing, engineering is another. The previous section ended with a promise. The physics works. The math checks out. Relativity says you can reach anywhere if you push gamma high enough. That's the theoretical possibility. But theory lives in a universe without constraints. Engineering lives in ours. There's an equation that defines what's actually possible with rockets. It was written in 1897 by a Russian schoolteacher named Konstantin Tsiolkovsky. He never built a rocket himself. He just understood the mathematics of throwing mass backward to push mass forward. His equation is simple. Delta V equals VE times the natural logarithm of m0 divided by mmf. Delta V is your velocity change. VEE is your exhaust velocity, how fast the rocket throws material out the back. m0 is your initial mass, ship plus fuel. mf is your final mass, just the ship after all fuel is burned. That's it. That's the equation that governs every rocket ever launched. The problem is that logarithm. It creates a relationship that destroys any hope of reaching relativistic speeds with conventional propulsion. Let me explain what logarithmic means in practical terms. To go twice as fast, you don't need twice as much fuel. You need all your fuel squared. 3 times as fast, all your fuel cubed. 10 times as fast, all your fuel to the 10th power. The numbers explode. By the time you're talking about relativistic speeds, all the fuel means more than the mass of planets. Chemical rockets, the kind we've used for every space mission in human history, have an exhaust velocity of about 4.5 kilometers per second. That's how fast the combustion products shoot out the back. With perfect engineering, with staging, with every optimization we know, chemical rockets can give you a delta V of maybe 10 kilometers per second. That's 0.003% of light speed. Not 3%, 0.003 of 1%. Ion drives are better. They use electricity to accelerate ions to about 50 kilometers per second. Much higher exhaust velocity, much better fuel efficiency, but tiny thrust. They take years to build up meaningful speed. Nuclear thermal rockets, where you heat propellant with a reactor instead of combustion, give you exhaust velocities around 10 kilometers per second. Better than chemical. Not by enough to matter for this discussion. Here's the question. What would it take to reach 10% of light speed using chemical rockets? 10% seems modest. It's still 100 times too slow to make relativity compress time by any meaningful amount. But let's try for 10% anyway. The speed of light is about 300,000 kilometers per second. 10% is 30,000 kilometers per second. Your exhaust velocity is 4.5 kilometers per second. Plug those numbers into Tsiolkovsky's equation and solve for the mass ratio. The answer is a fuel mass ratio of about 10 trillion to 1. Let that sink in. If your payload is 1 kilogram, a bag of sugar, you need 10 trillion kilograms of fuel. That's 10 billion metric tons. For comparison, the entire International Space Station, the largest structure ever assembled in space, has a mass of about 420,000 kilograms. You would need 23 million International Space Stations worth of fuel to accelerate 1 kilogram to 10% of light speed with chemical rockets. And you're still only at 10%, still nowhere near relativistic speeds, still experiencing barely any time dilation at all. Actually, that's not quite right. Let me try again. The problem isn't that we need more fuel. It's that more fuel makes the problem worse. Every kilogram you add is another kilogram you have to accelerate. You need fuel to carry fuel, to carry fuel, to carry fuel. The rocket equation isn't a challenge to overcome. It's a law that says, stop trying this way. Trying to reach light speed with conventional rockets is like trying to lift yourself by pulling on your own hair. The harder you try, the heavier you get, because you have to carry the fuel to carry the fuel to carry the fuel. Eventually, you're 99.9999% fuel and 0.0001% ship, and you still haven't reached a fraction of light speed. It's like a tax that increases exponentially. The first 1% of light speed costs X fuel. The next 1% costs 10X. The next costs 100X. By the time you reach 10%, you've spent more than the entire mass budget of your civilization, and you're still barely moving on cosmic scales. You're still in the realm where relativity barely notices you exist. This is the tyranny of the rocket equation. It's not that we need better rockets. Better rockets don't solve this. A rocket twice as efficient still hits the same wall, just a little farther out. 3 times as efficient, same wall. 10 times, same wall. The wall is mathematics. The wall is the logarithmic function that says exponential fuel for linear speed. There's something you need to understand about this limitation. It's not an engineering problem. You cannot solve it with better materials, better combustion chemistry, better anything within the framework of carrying your own propellant. The rocket equation's logarithmic nature means there's a hard wall for conventional propulsion. You cannot reach even 10% of light speed with any rocket that carries its own fuel, regardless of technological advancement. It's a physics problem, and physics problems don't care about human ambition. The previous section opened a door. Relativity says you can go anywhere, experience any journey within a human lifetime, if you can just reach high enough speeds. This section closes a different door. Conventional rockets cannot get you to those speeds. Not even close. Not within a factor of 1,000. Chemical rockets top out at 0.003%. Light speed. Ion drives might, with decades of thrust, reach 0.1% light speed. Nuclear thermal lands somewhere in between. All of them are so far below the speeds where time dilation becomes meaningful that they might as well be standing still. The universe remains vast. Human lifetimes remain brief. Relativity's promise remains theoretical. So what do you do when the rocket equation says no? When carrying your own fuel creates an impossible exponential trap? You stop carrying fuel. You start looking for ways to push a spacecraft that don't require carrying every gram of propellant from the start. You start asking what propulsion methods physics actually permits at relativistic speeds, because chemical rockets were never going to take us to the stars. The math has always said so. We've just been slow to accept it. The answer, in 1958, was to start throwing bombs. Project Orion was born at General Atomics in San Diego. Freeman Dyson and Ted Taylor led a team of physicists and engineers who asked a question nobody else was asking. What if we stopped trying to contain nuclear explosions and just used them raw? What if we dropped atomic bombs out the back of a spacecraft and rode the blasts? The idea sounds like something a kid would draw on a napkin. It sounds absurd, but the physics checked out, the engineering checked out, and they built it. Nuclear pulse propulsion is exactly what it sounds like. Throwing grenades out the back of your car and riding the explosions. It's absurd, it's violent, it's elegant, and it works. We tested it. The bombs were just never nuclear because treaties said no. Here's how Orion worked. You build a massive steel disc at the back of your spacecraft. That's the pusher plate. It absorbs the blast. Behind the pusher plate, you attach shock absorbers the size of telephone poles. Those smooth out the pulses, turn violent detonations into something the crew might survive. The spacecraft itself sits on top of this system. Inside, you carry thousands of nuclear charges, small ones. Each may be the size of a soda can. Every second, you drop a bomb out the back. It travels a few dozen meters. Then it detonates. The blast wave hits the pusher plate. The shock absorbers compress. The spacecraft lurches forward. Then you drop another bomb, another blast, another lurch. Imagine a spacecraft that hiccups nuclear fire. Every second, another detonation. Every blast, another few meters per second, added to velocity. It's not smooth. It's not comfortable. But it's honest. You want to move fast? Carry your energy density in the most concentrated form available. Nuclear warheads. The pusher plate concept is worth understanding. You're hammering a nail, except the nail is moving at thousands of kilometers per second, and the hammer is a nuclear weapon. Repeat 100,000 times. The plate itself was designed to ablate. Each blast vaporizes a microscopic layer of steel. That ablation is part of the momentum transfer. The plate gets slowly thinner, but you account for that. You make it thick enough to last the journey. The numbers were stunning. Orion's exhaust velocity would reach 10,000 kilometers per second, or higher. Chemical rockets max out at 5 kilometers per second. Ion drives might hit 100 kilometers per second after years of thrust. Orion would hit 10,000. That's not an incremental improvement. That's a different game entirely. With those numbers, you could accelerate a massive spacecraft to 5 or even 10% the speed of light. 5% light speed is 15,000 kilometers per second. At that velocity, you could reach Alpha Centauri in about 80 years. Still too long for a single human lifetime, but within reach of a generational ship. And Orion could carry hundreds of tons. You wouldn't be sending a tiny probe. You'd be sending a city. They didn't just design it on paper. They built test models, small ones, about a meter tall. The team conducted flight tests in the Nevada desert. They used conventional explosives instead of nuclear charges, but the principle was identical. Drop a charge, detonate it, ride the blast. The models flew. They demonstrated controlled ascent. They demonstrated stability. The footage still exists. You can watch a tiny metal cone hopping into the air on pulses of chemical explosives, proving that pulse propulsion works in practice. The project ran from 1958 to 1963. In those 5 years, the team designed spacecraft ranging from small interplanetary shuttles to massive ships capable of carrying thousands of people to other star systems. They calculated trajectories. They designed radiation shielding. They figured out how to protect the crew from the pulses. They solved problem after problem. And then 1963 arrived. The Partial Nuclear Test Ban Treaty banned nuclear explosions in the atmosphere, in space, and underwater. Orion required detonating nuclear weapons in space, thousands of them. The treaty killed the project instantly. There were other concerns too: fallout from launches, the optics of mounting nuclear weapons on spacecraft, the Cold War politics of appearing too aggressive. But the treaty was the final word. Physics didn't kill Orion. Engineering didn't kill Orion. Politics killed Orion. The designs were archived. The test footage was filed away. Freeman Dyson wrote about it years later with a kind of melancholy. He knew they'd had something real, not a fantasy, not a distant possibility, a propulsion system that could work with 1960s technology, a way to actually reach other star systems within human timeframes, or at least generational timeframes. And it died not because it was impossible, but because the world decided exploding nuclear weapons in space was a bad idea. That decision was probably correct, but it left us without a path forward. Orion remains one of the only propulsion concepts ever designed that could genuinely break free of the rocket equation's tyranny. You're not carrying inert propellant. You're carrying compact energy. Each bomb holds millions of times more energy per kilogram than chemical fuel. That changes the equation entirely. That makes the impossible possible. But even Orion has limits. 10% light speed is extraordinary compared to chemical rockets. It's a revolution, but it's still not relativistic. Time dilation at 10% light speed is barely noticeable. A trip to Alpha Centauri still takes 80 years on Earth and nearly 80 years for the crew. You're not experiencing the universe on human timescales. You're just getting slightly closer. To truly reach other stars within a human lifetime, to make relativity's promise real, you need something beyond even nuclear pulse propulsion. You need concepts that push even further into the exotic, and those concepts exist, on paper, in theory, in the quiet corners of physics where we ask what the universe actually permits. The most energy-dense fuel possible in this universe is antimatter. Not theoretically, not in science fiction, actually possible. Physics permits it. The laws of nature allow it. There is no denser fuel. There cannot be. This is the ceiling. When matter touches antimatter, they annihilate. Complete conversion. 100% of their mass becomes pure energy. Einstein's equation made real. E equals mc squared, with no losses, no waste, perfect efficiency. A kilogram of antimatter meeting a kilogram of matter releases 1.8 times 10 to the 17th joules. That's 43 megatons of explosive energy. About 3,000 Hiroshima bombs from 2 kilograms of fuel. A teaspoon of antimatter, annihilated with regular matter, releases enough energy to power a continent for a year. It's the most concentrated energy storage possible in this universe. There is no denser fuel. Physics says so. Compare that to fusion. Fusion converts about 1% of mass to energy. It's extraordinary compared to chemical reactions. But antimatter is 100 times more efficient. Chemical rockets, the kind we actually use, convert about 0.0001% of mass to energy. Antimatter isn't just better. It's playing a different game entirely. It's the sharpest possible knife. Here's the thing. We make antimatter right now. At CERN, at Fermilab, at other particle accelerator facilities around the world. It exists. We've produced it. We've contained it. We've studied its properties. This isn't speculation. The problem isn't that antimatter is fictional. The problem is cost and scale. CERN produces about 10 nanograms of antimatter per year, 10 billionths of a gram. That's a few trillion antiprotons. Sounds like a lot until you realize a gram contains 600 billion trillion atoms. Producing 1 gram at current rates would take 100 billion years, 1 gram. The universe is only 14 billion years old. We'd need to keep producing antimatter 7 times longer than the universe has existed to make a single gram. The cost makes it worse. Making antimatter today is like minting pennies that cost $1 billion each. We can do it. We just can't do it at scale. Every atom of antimatter requires particle accelerators, magnetic containment, massive amounts of input energy. Creating antimatter takes more energy than the antimatter will ever release. It's the ultimate expensive exotic fuel. Current estimates suggest producing 1 gram would cost about $62 trillion. That's more than half the GDP of Earth for 1 gram. Containment is its own nightmare. Antimatter can't touch matter. Touch means annihilation. You can't store it in a bottle. You can't pump it through pipes. Any contact with normal atoms and it's gone, converted to gamma rays and particle spray. The only option is magnetic containment, magnetic bottles. Powerful electromagnetic fields holding antimatter suspended in perfect vacuum, never touching the walls. We can do this in laboratories for tiny amounts, scaling it to kilograms of antimatter, keeping it stable during acceleration, during flight, during maneuvering. Nobody knows if that's even possible. Let's say we solve production. Let's say we solve containment. Let's say we have antimatter fuel in quantity, safely stored, ready to use. You still have the rocket equation. Even with antimatter, you're still carrying fuel. You still have mass. The rocket equation doesn't care how good your fuel is. It cares about the ratio, how much fuel versus how much payload. Antimatter helps. The efficiency is unmatched, but it doesn't eliminate the problem. You're just using a sharper knife to cut a thicker rope. To reach 99.9999% light speed with an antimatter rocket, you need fuel to payload mass ratios of hundreds or thousands to 1, maybe more. The exact number depends on your engine design, your exhaust velocity, how efficiently you direct the annihilation energy. But the principle holds. To go faster, you need more fuel. To carry more fuel, you need more fuel to accelerate that fuel. The spiral continues. Picture a spacecraft massing 100 tons. Your destination requires 99.9999% light speed. Even with perfect antimatter fuel and perfect engines, you might need 10,000 tons of antimatter and 10,000 tons of matter to annihilate it with. That's 20,000 tons of fuel to move 100 tons of ship, a ratio of 200 to 1. And that's optimistic. Some calculations suggest worse ratios. Some calculations suggest it's not achievable at all with rocket propulsion, even antimatter rockets. The energy requirements become absurd. Think about accelerating mass to relativistic speeds. Kinetic energy grows without limit as you approach light speed. At 99% light speed, kinetic energy is about 7 times rest mass energy. At 99.9999%, it's over 700 times rest mass energy. You're not just pushing the ship anymore. You're fighting the structure of space-time itself. Inertia doesn't level off. It grows and grows and grows. Will we ever make antimatter at scale? Honestly, we don't really know. That's the honest answer. We have the physics. We don't have the engineering. Maybe we never will. Maybe it's forever stuck as the theoretically perfect fuel we can only produce a few atoms at a time. Maybe there's a breakthrough coming. A new production method. A new containment system. Some insight we're missing. But right now, today, antimatter propulsion sits in the category of physically possible but practically absurd. There are concepts, designs on paper. The antimatter catalyzed nuclear pulse rocket use tiny amounts of antimatter to trigger fusion reactions, getting fusion energy with just a sprinkle of antimatter. Stretch your antimatter supply further, or antimatter beam core rockets. Direct the annihilation products straight out the exhaust. Maximum efficiency, no intermediate steps. These designs exist. They've been calculated. They might work, but they all require antimatter in quantities we can't produce. They all require containment systems we can't build. They all bump into the rocket equation eventually. Even antimatter has limits. To reach the highest gamma factors, to cross not just light years, but billions of light years in a human lifetime, you'd need fuel ratios that make the whole concept meaningless. 1,000,000 to 1, 10,000,000 to 1. At some point, you're not building a spacecraft, you're building a fuel tank with a tiny capsule attached, and even that might not be enough. This is the boundary. Antimatter represents the best possible chemical propulsion, the most energy per kilogram physics allows, and it's still not enough for the really big trips, still not enough to make the universe accessible on human scales. We've reached the edge of what carrying your fuel can do. Beyond this, you need something else, some other approach, some other physics. So what does all of this actually get you? Where can you go? Let's put real destinations to these numbers. See what's actually within reach if you can somehow build these ships and survive the acceleration. The universe becomes a map with travel times attached, but they're not the travel times you expect. Start with the closest star. Proxima Centauri, 4.24 light-years away, the nearest stellar neighbor we have besides the Sun. At gamma equals 10, that's 99.5% the speed of light. Your subjective trip time is about 0.42 years, 5 months, less time than a pregnancy. You'd leave Earth, experience 5 months of travel, and step onto another star system. But Earth time? 4.3 years. Everyone you left behind aged 4 years while you aged 5 months. That's nearby. That's the easy one. Push harder. Gamma equals 100. Now you're experiencing 0.042 years subjective. 15 days, 2 weeks, a long vacation. Proxima Centauri in 2 weeks from your perspective. Earth still ages 4.3 years. The trade becomes clear. You can compress your experience of the journey down to almost nothing. But the universe outside your ship doesn't care. It ticks forward at its own pace. Go bigger. The galactic center, 26,000 light-years away. The black hole at the heart of the Milky Way. At gamma equals 700, you experience 37 years subjective, most of a human lifetime, but doable. You could leave at 20, arrive at 57, still have decades ahead of you if you're lucky. Step off the ship and look at the supermassive black hole humanity has only ever seen in radio waves and grainy images. You were there. You saw it. But Earth, 26,000 years have passed. The pyramids would be ancient history when you left. They'd be eroded stumps when you arrived. Every language spoken at your departure would be dead. Every border redrawn 100 times. Every person you knew, their children, their children's children, for 300 generations, all dust. This is what the math allows. This is the trade. Here's the part most people don't realize. Andromeda Galaxy, 2.5 million light-years away, the most distant object you can see with your naked eye. At gamma equals 50,000, you experience about 50 years subjective. 50 years, a lifetime, but a single lifetime. You could board a ship as a young adult and arrive in Andromeda as an old person. Walk on a world orbiting a star in another galaxy. Look back and see the Milky Way as a spiral smudge in their sky. It's not impossible. The physics allows it. But Earth time? 2.5 million years. Think about that for a second. Boarding a ship in ancient Sumeria and stepping off in the modern day, except everyone you left behind is not just dead, but their entire civilization is geological history. The cities crumbled, the languages forgotten, the continents reshaped, and you aged 50 years. Every interstellar journey is a one-way ticket to the future. You leave in 2025, you arrive in 28,000 CE, or 2 million CE, or whenever. You can visit distant places, but you can never visit them and return home. Home is a when, not a where, and that when is gone the moment you accelerate. Your subjective lifetime becomes a bubble moving through space-time. Inside the bubble, 80 years. Normal life, breakfast and sleep and thoughts. Reading books maybe. Watching the ship's clock tick forward normally. Outside the bubble, empires rise and fall. Stars are born and die. Everyone who knew your name becomes dust. Then their dust becomes dust. Then even the memory of the civilization that remembered them fades into geology. This answers the question, how far could humans actually travel through space in one lifetime? From your perspective, as the traveler, almost anywhere. Nearby stars in weeks, the galactic center in decades, Andromeda in a human lifespan. At extremely high gamma factors, above 100,000, even distant galaxy clusters come within subjective lifetime reach. The edge of the observable universe is 46 billion light-years away. At gamma equals 1 million, you'd experience 46,000 years subjective. Still enormous, still longer than recorded human history, but not infinite, not impossible on evolutionary timescales. The limit isn't distance. The limit is what you're willing to lose. You can go anywhere. You just can't go home. Not to the home you left. That home exists in a time you can never reach again. You're trading space for time. Every light year of distance costs you years of Earth time. The exchange rate is brutal and non-negotiable. Someone watching you leave would see your ship accelerate, faster and faster, until it vanished into the black. They'd wait. 4 years for Proxima, 26,000 for the galactic center, 2.5 million for Andromeda. They'd be dead. Their species might be dead. But eventually, if they could watch, they'd see you arrive. From their frame, you took exactly as long as light would take, maybe a bit longer. From your frame, barely any time passed at all. Both are true. Both happen. The universe doesn't reconcile them. So the answer is everywhere and nowhere. You can reach distant galaxies in a lifetime, but you can't bring anyone with you who isn't on the ship. You can't send a message back. You can't change your mind halfway and return. Launch day is the last time you exist in the same when as everyone you've ever known. This is what the physics allows. This is what time dilation gives you and takes away. The universe is accessible. Every galaxy, every cluster, every structure we can see through telescopes, you could theoretically visit, but the cost is everyone and everything you leave behind. Not just dead, erased by time, forgotten, geologically gone. The nearby stars, though, those are different. Proxima Centauri, in 5 months, subjective, 4 years Earth time. Alpha Centauri, Barnard's star, Wolf 359. These are trips where Earth is still recognizable when you return. Still the same civilization, roughly. Same languages. Same governments maybe. People you knew would be older, but alive. Those trips are round trips. Those are journeys. Everything beyond about 10 light years becomes one way. The gap between your experience and Earth's experience grows too large. You're not traveling anymore. You're emigrating, permanently, to the future. Let's pick a destination and see what it actually takes to get there. Not hypothetically, not in theory. Let's take Andromeda and measure it against everything from a walking pace to relativistic speeds. Same galaxy, different velocities. The spread is absurd. Andromeda sits 2.5 million light-years away. That's 2.37 times 10 to the 19th kilometers. The number doesn't mean much until you start moving toward it. Start walking. 5 kilometers per hour. A comfortable pace, the kind of speed you'd maintain on a long hike. At that speed, reaching Andromeda would take 61.5 billion years. That's 4 times the current age of the universe. If you started walking when the universe began, 13.8 billion years ago at the Big Bang itself, you still wouldn't be a quarter of the way there. You'd need 4 universes, start to finish, to complete the walk. 4 cosmic cycles of creation, expansion, and heat-death, and you'd still be putting one foot in front of the other. Speed up, get in a car, drive at 100 kilometers per hour, highway speed, windows down, music on, endless road ahead. Andromeda is now 3 billion years away. That's longer than multicellular life has existed on Earth. You'd start your drive when our planet was a barren rock covered in bacterial mats and primitive slime. No plants, no animals, nothing with a brain. You'd arrive just in time to watch the first humans stand upright. Every single mile of that drive represents 30,000 years of Earth history. Every gallon of gas you burn moves you forward 1 million years through time. The entire journey from simple cells to conscious beings, and you're still holding the steering wheel. Fly instead. Take a commercial airliner. 900 kilometers per hour. Cruising altitude, smooth air, complimentary peanuts for 330 million years. That gets you from roughly the formation of the supercontinent Pangaea to now. Dinosaurs rise and fall. Mammals scatter across the globe. Ice ages come and go. Mountains wear down to plains, and you're in seat 14A the entire time. Use our fastest spacecraft. The Parker Solar Probe screams around the sun at 430,000 miles per hour. It's the fastest thing humans have ever built. At that speed, Andromeda is 3.8 million years away. You'd launch when our ancestors were Australopithecus, barely walking upright in the African savanna. You'd arrive, and they'd be flying spacecraft to meet you. The entire arc of human evolution, from ape to astronaut, fits inside the journey. Travel at light speed itself, the cosmic speed limit, the fastest anything can go, 2.5 million years. That's not a flaw in the universe. That's the design. Light speed is the maximum, and even at maximum, the cosmos is so vast that crossing it spans the entire history of human evolution. The light we see from Andromeda right now left when our ancestors were Homo habilis, chipping rocks into crude tools in East Africa. It traveled through empty space for 2.5 million years and arrived tonight so we could point telescopes at it. We've gone from stone tools to space telescopes in the time it takes light to cross the gap. Here's where it gets strange. You can push closer to light speed with enough energy. 99.9999% of the speed of light. Close enough that the difference is negligible for most purposes. At that speed, time dilation kicks in with a gamma factor, around 700. The universe ages 2.5 million years. You experience 3,571 years. Still not a human lifetime, not even close. You'd need generation ships, rotating crews, entire civilizations born and dying in transit. Near light speed isn't nearly enough. The phrase sounds fast. It isn't. Push harder. 99.9999999% of light speed. Gamma factor around 70,000. The gap between your speed and light speed is now a rounding error. The universe still sees 2.5 million years pass. You experience 36 years, one human lifetime. You board the ship as a young adult. You arrive middle-aged. Your knees hurt a little more. You've got some grey hair. Everyone you knew is dust. Their great-grandchildren's great-grandchildren are geological strata. But you're alive. You made it. That's the spread. Walking to Andromeda takes 4 universe lifetimes. Flying at maximum gamma takes 1 human lifetime. Same destination, different experience of time. The universe doesn't compress. You do. And Andromeda isn't even far. Not really. It's our nearest large neighbor. There are galaxies billions of light years away. Structures at the edge of the observable universe, 46 billion light years out. With high enough gamma factors, even those become reachable. The universe isn't closed to us. It's just locked behind time dilation. You can go anywhere. You just can't come back to the same when. So you could go almost anywhere. With enough gamma, even the edge becomes reachable in a human lifetime. The problem isn't physics. It's something else. Something harder to explain. Let me try anyway. How do you even conceive of distances this large? I'm not sure you can. Not really. You can know them mathematically. You can write them down. But can you feel 46 billion light years the way you feel a mile? I don't think so. No one can. And maybe that's okay. Maybe some things are too large for human minds. Even when we have the numbers, let me give you a way to approach it. Start counting. 1 light year per second. Just count. 1, 2, 3. Keep going. To reach Andromeda at that pace takes 29 days. Continuous counting. No sleep, no breaks. Almost a full month of your life spent just marking distance. And that's one galaxy, our nearest large neighbor. The thing you can see with your naked eye on a clear night. Keep counting at 1 light year per second toward the edge of the observable universe. You'll be counting for 1,475 years. That's longer than the printing press has existed, longer than gunpowder, longer than the Roman Empire lasted. You'd need to start counting before the fall of Rome and continue through every kingdom, every plague, every war, every invention right up to now. And you still wouldn't be done. Think about that. Here's another way. Count 1 light year for every heartbeat. Your heart beats roughly 2.5 billion times in 80 years. Every thump, another light year. That gets you to a nearby galaxy. Maybe 2 if you live long. To count to the edge of the observable universe at 1 light year per heartbeat would require 18 human lifetimes of continuous beating. 18 people, born and dying in sequence, their hearts marking cosmic distance. The universe is so large that even mapping it heartbeat by heartbeat exhausts multiple lives. Or try this. Live 1 subjective year for every light year to Andromeda. Just experience 1 full year of consciousness. Then move forward 1 light year. Repeat. You'd need 2.5 million years of continuous life. That's 10 times longer than humans have existed. 10 times longer than our entire species has walked this planet. And that's to 1 galaxy. The observable universe contains distances 18,000 times greater. You'd need to live longer than Earth has existed as a planet. You'd need to be older than the solar system, older than the sun itself. Andromeda has more stars than you have ancestors. Every human who ever lived, every parent and grandparent stretching back through every generation to the first cells that divided in primordial oceans. Andromeda has more suns than that entire lineage. Every single connection in the chain of life that led to you, every organism, every split, every branch, Andromeda outnumbers them all. And Andromeda is 1 galaxy in a universe of 2 trillion. 2 trillion galaxies, each one containing hundreds of billions of stars, some containing trillions. The numbers stop meaning anything after a while. They become sounds you make with your mouth, syllables without weight. The most distant galaxies we've observed are 13.4 billion light years away. The light left them shortly after the Big Bang. When that light began its journey, there were no planets, no atoms heavier than lithium, just hydrogen and helium and the first stars burning in the dark. The light traveled for longer than Earth has existed, longer than our solar system. It crossed a universe that was expanding the entire time, stretching the space it moved through. You could see that light with a telescope. It arrives at your eye after crossing most of the history of everything, and you're standing there, alive for maybe 80 years, looking at photons older than worlds. The observable universe radius is 46.5 billion light-years, not 13.8. The universe is 13.8 billion years old, but expansion stretched everything. The things we see at the edge aren't where they were when the light left. They've moved. The space between us and them has grown. They're 46.5 billion light-years away now, farther than light could travel in the age of the universe. You can't get there, even at light speed, even leaving right now. The space between you and those galaxies is expanding faster than you can cross it. But let's ignore that for a moment. Let's pretend expansion didn't matter. Let's pretend you could travel at any speed you wanted. Here's the thing that gets me. If you could go at any speed, ignoring physics entirely, unlimited acceleration, instant velocity changes, and you spent your entire 80-year lifetime just accelerating and traveling, never stopping, never slowing down, just covering distance as fast as physically possible, you'd still cross less than 0.0001% of the observable universe. Even infinity speed isn't enough time. The universe isn't just large. It's large in a way that makes human lifetimes irrelevant. You're a mayfly to cosmic distance, here for a flicker, gone before anything significant happens. You could spend every second of your life moving as fast as the laws of reality allow, and you'd barely leave the neighborhood, the galaxy next door. Maybe a small cluster if you push it. The rest is out there, waiting, unreachable, not because the technology doesn't exist, unreachable because there isn't enough time in a human life to cross it, even if you bent physics to its breaking point, even if you rode time dilation all the way down to subjective minutes. The universe is too big and you are too brief. 46 billion light-years in one direction, 46 billion in the other, 92 billion light-years across, and you get 80 years, maybe 90 if you're lucky. That's the deal. That's what we're working with. Every single one of those light-years is a place, a volume of space containing something. Maybe just hydrogen atoms and darkness, maybe a star, maybe a planet, maybe something we don't have words for yet, and almost all of it will never be visited, not by you, not by anyone from Earth, not in any future you can imagine. You can go far. With the right ship, you can go very far, farther than seems possible right now. But far is still nothing compared to everything. The reachable universe is a tiny bubble around us, a sphere, maybe a few million light-years wide if we're generous with the technology. Beyond that, it's just light we can see, galaxies we can photograph, structures we can catalogue and name and wonder about. We'll never walk there. We'll never send a probe. We'll never know what's happening there right now. We'll only ever see the past. Light that's been traveling so long, the source might not exist anymore. We're looking at ghosts, echoes, things that were, and that's just the observable universe. The part we can see, the actual universe, is bigger, maybe infinite. We don't know. We can't know. Our view ends at the distance. Light has had time to travel. Beyond that is just speculation. More space, more galaxies, more of everything, stretching on forever in ways we can't measure or confirm. You are here, on this planet, in this moment, looking up at a sky full of things you'll never reach. That's not sad, that's just scale. The universe doesn't care what we find convenient. It simply is, large beyond feeling, old beyond imagining, and we're part of it anyway. We've been talking about reaching distant galaxies, about percentages of light speed, about gamma factors stretching time and space, but there's a wall we haven't hit yet, a limit that isn't about fuel or engineering or how clever we build our spacecraft. It's deeper than that, more fundamental. You can't just keep accelerating forever. The universe won't let you. Here's why. As you approach light speed, acceleration gets harder. Not just harder, exponentially harder. Every bit of extra speed costs more energy than the last bit. The energy requirement grows without bound. At exactly light speed, it becomes infinite. You'd need infinite energy to push matter to exactly the speed of light. The universe doesn't have infinite energy, neither do you. So you can't get there, ever. You can get close, really close, but never all the way. Approaching light speed is like trying to climb an infinite mountain. Every step up, the mountain grows taller. You can always take one more step, but the summit keeps receding. You climb forever and never arrive, because arrival is infinitely far away, no matter where you are on the slope. The math shows this clearly. Relativistic kinetic energy follows a formula. Kinetic energy equals gamma minus 1 times rest mass energy. When gamma equals 2, that's 86.6% of light speed. Your kinetic energy equals your rest mass energy. You've put in as much energy as the total mass of your ship converted to pure energy. That's a lot. When gamma reaches 10, you're carrying 9 times your rest mass in kinetic energy. At gamma 100, it's 99 times your rest mass. The numbers grow without mercy. Let's look at what this means in practice. Getting to 90% of light speed from rest takes a certain amount of energy. Call it x. Doubling your speed from 90% to 95% doesn't take another x. It takes 2.4 times x. More than doubling. You're not even adding that much velocity, but the energy cost explodes. Going from 99.9% to 99.99% of light speed requires 3.16 times more energy than it took to reach 99.9% from rest. You're adding 0.09% more speed, and it costs 3 times everything you've already spent. Each decimal place closer to light speed requires roughly 10 times more energy. First decimal place, manageable. Second decimal place, expensive. Third decimal place, costs a moon. Fourth decimal place, costs a planet. Fifth, costs a star. Sixth, costs a galaxy. You can keep adding decimal places forever. 99.9999999%. As many nines as you want. But eventually, you run out of universe to pay the bill. It's like compressing a spring that gets exponentially stiffer. The first inch is easy. The second inch takes more force. By the 10th inch, you need the strength of a hydraulic press. By the 100th, you need the energy output of a sun. The spring never runs out of stiffness. It just keeps demanding more. You compress it another 1,000th of an inch, and suddenly you need the energy output of a galaxy. Another 1,000,000th of an inch after that, and you've exceeded the total energy available in the observable universe. The spring doesn't care. It'll keep resisting. Forever. This is an asymptote, a mathematical barrier you approach but never cross. You can get arbitrarily close to light speed, as close as you want, in theory. But exactly at light speed, that's forbidden. Not by law or physics we might one day overcome. By the structure of space-time itself, no finite energy can accelerate matter to exactly the speed of light. The closer you get, the more each additional increment costs. And the cost rises without limit. Here's something most people don't think about. At extreme velocities, your spacecraft becomes dangerous just by existing. A single gram of matter accelerated to 99.99999% of light speed has a gamma factor around 70,000. That 1 gram carries kinetic energy equal to the Tsar Bomba, the largest nuclear weapon ever detonated. 50 megatons, a gram. At those speeds, a speck of dust hits with the force of a strategic nuclear weapon. Your spacecraft isn't just traveling, it's a relativistic weapon. Anything in its path gets vaporized, not by some futuristic ray gun, just by impact, by the sheer energy of motion. That's why those final decimal places matter so much. It's not just about going faster, it's about the energy you're carrying, the danger you represent, the cosmic absurdity of trying to push matter that close to the ultimate speed limit. You're fighting the fabric of reality, and reality always wins. This means there are practical limits. Even with perfect fuel, perfect efficiency, perfect everything, you can only push so far. Building a ship with gamma 10,000 is theoretically possible. You just need 10,000 times the rest mass energy of your entire spacecraft, in fuel, which you also have to accelerate, which makes the problem worse. Gamma 100,000? Forget it. You'd need to harvest entire stars, maybe entire galaxies, and you still wouldn't be at light speed. You'd still be some tiny fraction away from the limit, some vanishingly small distance from the asymptote, close enough that it makes no practical difference, but mathematically, eternally, infinitely far from exact. So when we talk about reaching distant galaxies, we're always talking about some percentage of light speed, some gamma factor. Never the full thing, never 100%. The best we can hope for is high enough that time dilation becomes significant, high enough that a human lifetime stretches into subjective centuries. Gamma factors in the hundreds, maybe thousands if we're wildly optimistic about future technology, but not millions, not billions. Those numbers require energy budgets that don't exist, resources we can't gather, physics we can't cheat. The universe set a speed limit. Then it made sure you can never quite reach it. You can spend everything trying, every joule of energy available, every star in the galaxy converted to fuel, and you'd still be some infinitesimal amount short, still climbing that infinite mountain, still compressing that endless spring. The summit recedes, the spring resists, the asymptote remains. You get close, you get closer, but you never arrive. That's not a limitation of technology. That's just how space-time works. The final speed is always just out of reach, forever. The universe set a speed limit. Then it made the limit unreachable. Then it added one more rule, one that makes all the engineering irrelevant, all the energy calculations meaningless, all the time dilation strategies futile. Space itself is expanding, not expanding into anything, just expanding. The fabric of the universe stretches. Galaxies move apart, not because they're traveling through space, but because the space between them grows. More space appears between any 2 points over time. The farther apart two objects are, the more space sits between them. The more space between them, the faster they separate. This isn't new motion. This is the structure of reality changing underneath everything. The expansion rate has a name, the Hubble constant. Roughly 70 kilometers per second per megaparsec. A megaparsec is about 3.3 million light years. That means for every 3.3 million light years of distance, space expands at an additional 70 kilometers per second. Nearby galaxies recede slowly. Distant galaxies recede faster. Very distant galaxies recede very fast. And far enough away, galaxies recede faster than light. Space expansion is like baking bread dough with raisins embedded. As the dough rises, raisins move apart, not because they're moving through the dough, but because the dough itself is expanding. Nearby raisins separate slowly. Distant raisins separate faster. Far enough away, raisins recede faster than you could ever walk through the dough to reach them, even if you walked at the dough's maximum speed. The dough betrays you. You can walk forever. You can walk at the fastest possible speed, and certain raisins will still move away faster than you can approach. That's what happens with galaxies. There's a boundary, a distance where the expansion velocity equals the speed of light. Beyond that boundary, space carries objects away faster than light travels. This boundary sits at roughly 16 to 17 billion light years from us. It has a name, the cosmic event horizon. Everything beyond that horizon is unreachable, not because we lack the technology, not because we lack the energy, but because the destination recedes faster than we could ever travel toward it, even at light speed. Imagine running on a treadmill that gets faster the farther forward you look. Nearby sections are manageable. Middle sections are harder. Far sections run faster than you can possibly move. There's a point where the treadmill is moving backward faster than your maximum speed. Beyond that point, even infinite stamina won't get you there. The ground itself defeats you. You can run forever and never cross that line. The treadmill wins. It's a race where the finish line runs away. You run toward it at the maximum possible speed, light speed, and the finish line recedes at equal or greater speed. Not because it's fast, but because the racetrack itself is stretching. You can run forever and never get closer. Physics has disqualified you before the starting gun fired. This isn't theoretical. This is happening right now. A photon leaves Earth, travels toward a distant galaxy beyond the event horizon. The photon moves at light speed, maximum velocity. Nothing goes faster, but space expands between the photon and its destination. Every second, more space appears. The photon crosses that new space. More space appears. The photon crosses it. More space appears. The photon makes progress through local space, but loses ground relative to the destination. It's like climbing a down escalator that moves faster than you climb. You step up, the stairs carry you down. You step again, the stairs win. You climb forever and descend. The photon never arrives. It travels for eternity through expanding space and never reaches its target. If light can't get there, nothing can. This boundary sits at 16 to 17 billion light-years. That's the distance where recession velocity equals light speed. Beyond that, recession exceeds light speed. Those regions are causally disconnected from us, forever. No signal from us will ever reach them. No signal from them will ever reach us. We share a universe, but not a future. They exist in a part of space-time we cannot touch. And here's the strange part. We can see galaxies beyond the event horizon. We're looking at them right now, through telescopes. Their light reaches us. We can measure their spectra, count their stars, watch them rotate. These galaxies exist beyond the boundary where nothing can travel, yet we see them clearly. The light left those galaxies billions of years ago, back when they were closer, back when the space between us and them was smaller, back when they hadn't yet crossed the event horizon. That light has been traveling toward us ever since, fighting against expansion, crossing newly created space, taking billions of years to close the distance. It finally arrives. We capture it with mirrors and sensors. We study it, but the galaxies themselves have moved on. Space carried them away while their light traveled toward us. They crossed the event horizon while we weren't looking. They're gone now, beyond reach. We're seeing ancient history, light from a place that no longer exists in our causal universe. Those galaxies are still out there, still shining, still full of stars, but they're receding faster than light. We will never receive another signal from them that left after they crossed the horizon. We're watching the last photons, the final transmission, a goodbye we didn't know was happening. I think about this sometimes. There are galaxies we can see right now with telescopes that we will never reach. Not because we're not advanced enough, not because we don't have the right technology, but because the universe itself says no. Those places are visible but untouchable, like reflections in a lake. You can see them. You can't ever go there. The universe showed them to us and then locked the door. The cosmic event horizon is not the same as the observable universe. The observable universe extends to about 46.5 billion light-years. That's the radius from which light has had time to reach us since the beginning. The event horizon is much closer, 16 to 17 billion light-years. The observable universe is what we can see. The event horizon is what we can reach. The gap between them is vast, and it's full of galaxies we can observe but never visit. The event horizon does grow over time, slowly. As the universe ages, slightly more space becomes reachable, but the acceleration of expansion complicates this. Dark energy drives galaxies apart faster over time. Regions beyond the current horizon are not becoming reachable. They're being pushed farther away. The door is closing, not opening. Anything beyond the current cosmic event horizon will remain beyond it forever. This is the ultimate ceiling, the final answer to how far humans could travel in one lifetime, or a million lifetimes, or any number of lifetimes. You can solve propulsion. You can harvest the energy of stars. You can achieve gamma factors that stretch time into unrecognizable shapes. You can do everything right, and you still can't go past 16 to 17 billion light-years. That's the boundary, not drawn by technology, not drawn by energy, drawn by space-time itself. The horizon runs away. You chase it. It recedes. You run faster. It recedes faster. You reach maximum speed. It's already gone. The universe gave us a vast playground, billions of light years in every direction, trillions of galaxies, countless stars. Then it drew a line and said, "Not past here." This far, no farther. The dough expands, the treadmill accelerates, the finish line runs, and we stand here, looking out at a universe we can see but cannot fully reach. 16 to 17 billion light years. That's the number. That's the maximum distance. That's how far humans could actually travel through space, assuming we could somehow get there at all. But what would it actually feel like to be inside that spacecraft, hurtling through the cosmos at speeds that bend reality itself? Let's step inside. Your clock ticks normally. Your heart beats normally. You breathe, you think, you age at the pace you've always known. Time hasn't slowed down for you. You pick up a book and read it at normal speed. You eat a meal. You sleep for 8 hours, and 8 hours pass. This is crucial to understand. You're not frozen. You're not in suspended animation. You're just living. It's everything outside that's gone mad. Imagine watching the universe in time-lapse from inside a bulletproof bubble. Outside, stars flicker like candles in fast forward. Galaxies swirl and collide in seconds. Civilizations rise and collapse between your heartbeats. Inside, you're reading a book, eating a meal, sleeping normally. Time hasn't stopped for you. It's sprinting for everyone else. You're not frozen. They're racing. You glance out the window. The view is wrong, distorted in ways that don't match anything you've experienced before. The stars ahead have moved, not just slightly. They've all crowded into a bright cone directly in front of you. Most of the sky appears behind you now, even though those stars should be scattered everywhere. This is aberration. Light itself can't keep up with your motion. The universe compresses forward. Everything you're moving toward squeezes into a smaller and smaller circle. The visual distortion is like driving into a snowstorm where all the snowflakes come from directly ahead, and the road behind you is dark and empty. Except the snowflakes are stars, and they're blue shifted into deadly radiation. You're not looking at the universe anymore. You're ramming through it at speeds that turn light itself into a weapon, because the colors are wrong too. The stars ahead aren't white or yellow or red anymore. They've shifted blue, deep blue, ultraviolet, beyond ultraviolet, into frequencies your eyes can't even register. The Doppler shift has pushed their light up the spectrum. Every photon is compressed, its wavelength shortened, its energy increased. The stars behind you have done the opposite. They've reddened, dimmed, stretched into infrared and beyond. The rear view is dark. Almost everything is ahead now, and it's all the wrong color. At extreme speeds, something stranger happens, something nobody warned you about. The cosmic microwave background radiation, the afterglow of the Big Bang itself. Normally, it's a harmless 2.7 Kelvin glow, the coldest, oldest light in the universe, barely there at all. But you're moving so fast that it blue shifts. The wavelength compresses, the energy climbs. That ancient, gentle warmth becomes visible light, then ultraviolet, then X-rays, then gamma rays. At high enough speeds, the cosmic microwave background radiation blue shifts into lethal gamma rays hitting you from ahead. The universe's oldest, coldest light becomes a death beam simply because you're moving fast enough. Space itself becomes hostile. The very fabric of the cosmos turns against you, not because it's malicious, because you're moving in ways nothing was meant to move. The interstellar medium does the same. Hydrogen atoms, dust grains, particles floating harmlessly in the void. When you hit them at relativistic speeds, they're not particles anymore. They're radiation, a particle beam slamming into your hull with energies that would make a particle accelerator look gentle. Every atom becomes a bullet. Every speck of dust becomes a bomb. You're isolated in ways no human has ever been isolated before. You send a message home after one subjective year. At a gamma factor of 50,000, Earth has aged 50,000 years while you experienced one. If they reply instantly, their message takes another 50,000 Earth years to reach you, but you've only been traveling for 2 subjective years total. You receive their reply before you've even finished your journey, but it's from a civilization 100,000 years older than the one you left. Every message is archaeological. You can't have a conversation. You can't ask for advice. You can't hear about what's happening back home in any meaningful sense. By the time you receive word that someone you loved has died, entire civilizations have risen and fallen on Earth. By the time you send condolences, the language you wrote them in might be extinct. Communication lag isn't just inconvenient, it severs you completely. You watch through your window as stars are born and die, not over billions of years, over days, weeks. The outside universe is in fast forward. A blue giant ignites, burns through its fuel, and explodes as a supernova before you finish breakfast. Globular clusters drift and dissolve. Galaxies that were spiral when you left have merged into ellipticals by the time you look again. You're watching deep time at normal speed. The psychological weight of this is hard to grasp. You're not in stasis. You're conscious, aware, experiencing every moment. But you're living in a different time frame than the rest of reality. You're a ghost moving through a universe that's aging faster than you can comprehend. Everyone you knew is gone. Not just dead, gone beyond death. Their grandchildren's grandchildren's grandchildren are dust. The nations they lived in are footnotes in archives you'll never read. There's no going back. Not really. Even if you turned around, even if you returned to Earth, tens of thousands of years would pass there. Hundreds of thousands. Millions. Depending on how far you went. You'd arrive at a planet that might not remember you ever left, that might not have records of your species anymore, that might not be habitable at all. You're untethered from history itself, floating in a bubble of slow time, surrounded by a universe sprinting toward its distant end, and you're only halfway there. You arrive at the destination. Let's say you traveled to Andromeda. You aimed for a distant star cluster in that galaxy, a place no human eye has ever seen up close. Your relativistic ship carried you there at incredible speeds. Time dilation worked exactly as predicted. You experienced about 50 years of subjective time. You launched young. You arrive middle-aged. You've lived a full adult life in transit. You've read every book in the database. You've formed relationships with the crew. You've changed as a person. 50 years feels like 50 years. But Earth aged 2.5 million years while you were gone. 2.5 million years. That's not ancient history. That's geological time. The entire span from the first stone tools to the present day fits into that window. Twice. The continents have moved. Mountain ranges have risen and eroded. Ice ages have come and gone dozens of times. Species have evolved and gone extinct by the thousands. Your home is gone. Not destroyed, just unrecognizable. The civilization that built your ship no longer exists. The nations that funded your mission dissolved millennia ago. The languages you speak are dead. The cities you remember are buried under sediment or worn to dust. The people who waved goodbye are fossils. Their descendants are fossils. The descendants of those descendants might not even be human anymore. Think about what happens on shorter journeys. Say you only travel a few hundred light years. You visit a nearby star cluster and return. The round trip costs 1,000 Earth years, maybe 10,000, depending on your speed. You launch when humanity is building skyscrapers and flying airplanes. You return when they're doing something you can't even conceptualize. Imagine launching as Columbus, when Europe thought the Earth might be flat, and arriving in a world of space colonies and post-human consciousness. Except, multiply that cultural gap by 1,000. You left speaking a language no one remembers. You return with knowledge no one needs. You're not a hero, you're a curiosity, a relic, a person-shaped fossil from an age before history began. Travel farther and it gets worse. The galactic center is about 26,000 light-years away. A round trip, even at extreme relativistic speeds, costs hundreds of thousands of years of Earth time. You might experience only decades. But you return to a planet where Homo sapiens might not exist anymore, where the entire archaeological record of your species is a thin layer in the rock, where your DNA, if it survived at all, is studied by beings you wouldn't recognize as descendants. Travel to another galaxy, and the numbers become absurd. Andromeda is 2.5 million light-years away. A round trip costs 5 million Earth years. You leave Earth when humans are living in cities and return when Earth is a barren rock orbiting a dying sun. You aged 100 years. Earth aged 5 million. Your entire species lived, thrived, went extinct, and was fossilized while you were gone. You're not returning home. You're visiting a grave world that happened to be where home used to be. The sun has about 5 billion years left before it dies. 5 billion years sounds like forever, but if you travel far enough, fast enough, you can outlive it within your own lifetime. You can launch under a yellow sun and return to a red giant. You can watch your home star bloat and consume the inner planets. You can arrive at an Earth that doesn't exist anymore, vaporized or ejected from the solar system entirely. Here's the part most people don't think about. The return journey isn't a homecoming, it's a museum visit. If you're lucky, there's a monument commemorating your launch. If you're unlucky, there's nothing, not even ruins. The continents have drifted into new configurations. The species have evolved or died. The sun has changed color. You recognize nothing, and nothing recognizes you. And you can't choose not to return. Well, you can, but that doesn't solve the problem. It just changes it. If you arrive at Andromeda after 50 subjective years, you're still stranded in time. The Andromeda you arrive at exists 2.5 million years after the Earth you left. There's no version of this where you stay connected to your origin point. The moment you accelerate to relativistic speeds, you sever that connection permanently. Even communication doesn't work. You can't call home. By the time your message arrives, centuries have passed on Earth. By the time they respond, centuries more. A conversation takes millennia. By the third exchange, everyone who started the conversation is dead. By the 10th exchange, their civilization might be gone. You become a ghost, not metaphorically, literally. You exist outside the normal flow of time. You're causally disconnected from the history you left behind. You're a time traveler moving forward, watching the universe age around you, unable to stop or slow down. You're conscious and aware, but you're living in a pocket of slow time while everything else sprints ahead. This is the surprise nobody tells you about relativistic travel. A journey to any destination beyond our local galactic neighborhood is effectively one way. Even if you turn around immediately, even if you point your ship back toward Earth the moment you arrive, because the Earth you return to has aged so much that it might as well be a different planet. The "you can never go home" isn't metaphorical, it's literal causality. Time dilation doesn't just separate you from the people you knew, it separates you from the epoch you knew, from the version of reality you came from. You don't lose your family, you lose your era. The human cost is hard to articulate. You volunteered for this. You knew the numbers. You accepted that everyone you loved would die while you were gone. But accepting it intellectually and experiencing it are different things. You arrive at your destination and realize there's no one to report back to, no one waiting for your data, no one who cares about the discoveries you made. The questions you set out to answer have been answered, forgotten, and replaced by new questions 100 times over. You're not an explorer anymore, you're a remnant. This is the fundamental trade-off of extreme space travel. Distance for time, exploration for connection. You can go far, farther than seems possible, but you pay for every light year with years of Earth time. The exchange rate is brutal, and it only gets worse the farther you go. The universe doesn't care what you find convenient. It doesn't care that you want to explore and return. It doesn't bend its rules for human ambition. You can travel across galaxies in a single lifetime, but the lifetime that passes back home will be measured in geological ages. You can see wonders no one else will ever see, but you'll see them alone, untethered from the world that made you. And when you arrive, if you arrive, you'll find yourself in a future that has no place for you, a time that moved on without you, a universe that forgot you left. So why does the universe have this speed limit at all? Why does reality draw a line at exactly 299,792,458 meters per second and say, no faster? It seems arbitrary, like a rule someone made up, but it's not arbitrary, it's foundational. The speed of light isn't really about light at all. The speed of light isn't the speed of light. It's the speed of cause and effect. It's the universe's way of keeping events in order, of making sure that actions come before consequences, that causes precede effects. Without the speed limit, time becomes meaningless. You could arrive before you left, receive messages from your own future, undo your own birth. The universe says no. Light speed is the speed of coherent reality. It's the maximum rate at which information can travel from one point to another. Not just messages or signals. Information in the deepest sense. The fact that something happened. The consequence of an event rippling outward through space-time. That propagation has a speed limit, and that limit is c. Here's what makes this strange. The speed limit isn't a property of light specifically. It's a property of space-time itself. Light just happens to be massless, so it travels at the universe's maximum speed. But anything massless would do the same. Gravitational waves travel at c. Certain theoretical particles called gluons travel at c. The speed limit is baked into the structure of reality. Light is just the messenger we notice most. Think of space-time as a fabric with a maximum propagation speed for disturbances. Snap your fingers and the disturbance spreads outward, but only so fast. That speed is c. If disturbances could spread infinitely fast, every point would affect every other point simultaneously. The universe would be a single entangled instant with no separation, no time, no narrative. The speed limit creates distance. Distance creates time. Time creates stories. Without the speed limit, causality breaks. Effects could precede causes. You could observe an event before it happened. You could intervene in your own past. The timeline would shatter into fragments with no consistent ordering. Events wouldn't happen in sequence. They'd just happen, all at once, in no particular relationship to each other. The universe would be incoherent. It's like the universe's frame rate. Reality processes at c. Anything happening faster than c would require the universe to process information faster than its own clock speed, which is incoherent, like asking a computer to calculate something before it receives the input. The operation doesn't make sense. The speed limit isn't arbitrary. It's structural. Particles with mass can't reach c because doing so would require infinite energy. As you accelerate closer to light speed, your mass effectively increases. Not your actual rest mass, but your relativistic mass. The resistance to further acceleration. The closer you get to c, the more energy you need to go faster. At exactly c, the energy requirement becomes infinite, which means impossible. Massless particles don't have this problem. They have no rest mass, so they start at c and stay there. They never accelerate. They're born moving at light speed and can never slow down. It's not that they're going fast, it's that they exist only at that speed. For a photon, there is no experience of time. From its perspective, emission and absorption happen simultaneously. It doesn't travel, it just is. This is the universe protecting itself. The speed limit enforces cause and effect relationships across all of space-time. It makes sure that events happen in a consistent order, that past stays past and future stays future, that you can't reach back and unwrite your own history. And here's the part that surprises people. If faster than light travel were possible, it would also enable time travel into the past, not as a side effect, as the same phenomenon. Due to the relativity of simultaneity in different reference frames, moving faster than light in one direction is mathematically equivalent to moving backward in time in another frame. FTL and time travel are the same problem. Banning one automatically bans the other. The universe's speed limit protects causality, not just space. Humans really want to break the speed limit. We want wormholes, warp drives, hyperspace, anything to bypass the rules. It's very human. We see a law of physics and think, surely there's a loophole. But maybe, just maybe, the universe isn't being unfair. Maybe the speed limit is what keeps reality from collapsing into incoherent chaos. Maybe we should be grateful the universe has rules, even if they're inconvenient for our galactic road trip plans. The constraint feels cruel when you're trying to cross a galaxy, when you're calculating travel times and realizing how far apart everything is. But the constraint is also what makes travel meaningful, what makes distance real, what makes journeys matter. Without the speed limit, distance wouldn't exist. Not in any meaningful sense. If information could travel instantly, everywhere would be here. Every event would be now. There would be no separation, no waiting, no journey, just immediate connection to everything, everywhere, all at once. Which sounds appealing until you realize it would erase the concept of location entirely. You can't travel somewhere if there's no difference between here and there. The speed limit defines the shape of the universe. It creates the space between things. It enforces the separation that makes individual locations possible. It sets the pace at which events unfold. It turns the universe from a dimensionless point into a vast stage where things happen in sequence, where causes lead to effects, where stories can be told. The speed limit isn't a fence keeping us in. It's the foundation making the universe coherent. It's why we can ask how far we could travel in a lifetime. Without it, the question wouldn't make sense. Distance wouldn't mean anything. A lifetime wouldn't mean anything. We'd exist in a timeless, spaceless instant where nothing happens because everything already happened. The universe has rules, not because it wants to stop us, but because without those rules, there wouldn't be a universe to explore. There wouldn't be an us to do the exploring. The speed limit is what makes reality real. The universe has rules. They shape what's possible, and those rules give us an answer to our question. How far could humans actually travel through space in one lifetime? Roughly 16 to 17 billion light years. That's the cosmic event horizon, the edge of everything we can see, a distance so vast that light itself, traveling for longer than Earth has existed, couldn't cross it. You could visit the earliest galaxies, the most distant quasars, the boundaries of everything observable. You could travel to the edge of forever, but you'd be utterly alone. Every person you loved would be dust. Every city you knew would be geology. Every language you spoke would be extinct. You'd cross the universe and lose the world. That's the trade physics offers. Everywhere, but never home. Remember those photons from Andromeda? The ones that left before humans made fire? You could travel back along their path, retracing 2.5 million years of light in a handful of decades. You could stand in Andromeda and look back toward the Milky Way, seeing it as it was when you left. The light would show you home, but the Milky Way you're seeing is the past. The Milky Way that exists now, in your arrival moment, has aged millions of years. You can see where you came from, but you can never touch it again. Time has locked the door. Reaching those distances is possible if you can accelerate to extreme speeds, gamma factors of 200,000 or more. At those velocities, time dilation compresses your subjective experience down to decades, while the universe outside ages billions of years. Physics doesn't forbid it. The equations work. But every light year you travel forward in space pushes you millions of years forward in time. You lose Earth. You lose your civilization. You lose your entire temporal context. You trade your home era for distance. The final irony sits at the heart of this. Achieving the speeds needed to cross cosmic distances makes you relativistically immortal from Earth's perspective. You're moving so fast that Earth time nearly stops for you. You wanted to live forever. Physics granted your wish. But the Earth you're immortal relative to no longer exists. You've become functionally timeless by escaping into deep time. Forever is empty. The universe offers you a choice. Stay home and watch the stars, or become a star yourself. A lone traveler moving so fast that you're no longer part of the same time as anything else. You can go anywhere. You just can't bring anyone with you. Not even your own history. The ultimate limit isn't energy. It isn't technology. It's the cost of leaving everything behind forever. So how far could we go? Almost anywhere. How much would it cost? Everything. Maybe that's the point. Maybe the universe is telling us something with these rules. You can explore, or you can belong. You can see the distant lights, or you can stay near the warmth of home. Both are valid. Both are beautiful, but you can't have both. The universe makes you choose. If you enjoyed this journey through space-time, consider subscribing. There are more explorations waiting.